Video number 3. So two events A and B are independent if knowing that one event occurs does not change the probability that the other occurs. If A and B are independent, then the probability of A and B, and notice when we talked about disjoint events, let me hop back here, whenever we use the term or, then that meant that we were going to be adding our individual probabilities. And now notice the difference here. We're going to be using the term and. If we want event A and B to happen, then in the end we're going to end up multiplying those events. Okay, but we can only do this if A and B are really independent events. You have to be told that that is true in order to multiply the individual probabilities there. This is called the multiplication rule for independent events. So first, we're going to classify the following events as independent or dependent, and then we're also going to calculate their probabilities. So imagine we have a deck of cards and we want to draw an ace. We're going to put it back in the deck, shuffle the deck, and then draw another ace. Okay, so drawing the first ace and drawing the second ace, are those two events independent or are they dependent? Well, drawing the first ace has a 4 in 52 chance. There's 4 aces out of 52 cards altogether. So whenever I draw that ace, there's 3 left in the deck. But notice here, I said I'm going to put it back in and then reshuffle and then draw another ace. Well, what's the probability that I draw another ace when I put the first one back in? Well, there's still 4 out of 52 chances that I'm going to pull another ace because I could re-pull the same exact ace. Okay, the first time I could have pulled an ace of hearts, and the second time I could have pulled again the ace of hearts. So the probability of an ace and an ace ends up being a 1 in 169 chance. Now you might go, well, wait, how did you get 1 out of 169 when you have these two probabilities of 4 out of 52? Well, 4 out of 52 really simplifies to be 1 in 13. And since these two events are independent, then I may multiply together their probabilities, and 1 times 1 across the top is 1, and 13 times 13 across the bottom is 169. Okay? So number 3 here, it says draw a heart, shuffle, then draw a diamond. So I want to find what's the probability of getting a heart and a diamond. Well, first off, are these two events independent? So if I drew a heart, and then I shuffled the deck, and then picked another card. Well, what's the probability that I drew a heart? Well, there's 4 suits times 13 of each of those suits. So I have a 13 out of 52 chance of pulling a heart. But notice there's one little difference here compared here to the ace problem. I don't put the heart back. Okay? So now is drawing a diamond 13 out of 52? It's not 13 out of 52. It's 13 out of, well, how many cards are left since I didn't put the original heart back? Well, now there's only 51. At this point, you can multiply these two things together, okay? So we can take 1/4, which is our 13 out of 52. That's where I'm getting this from, times 13 out of 51. So you can still multiply two events together as long as you take into consideration if events are really independent or not. So 1/4 times 13/51 makes 13 out of 204, simplified. Okay, so just because two events are not independent doesn't mean you can't calculate a probability. It just means that you cannot multiply together their individual probabilities. Again, I could not have taken 1/4 and multiplied it by another 4th because that probability for the second diamond, or for this diamond here, was not equal to a 4th because I didn't put the first heart back. If this said replace it, shuffle, and then draw a diamond, then it would be a 4th times a 4th, which is a 16th. So it is not uncommon for people to confuse the concepts of mutually exclusive events and independent events. Now, independent, we said earlier, was that the event of one outcome has no effect on the outcome of another event happening. Now, mutually exclusive means that if one event happens, then the other cannot happen. Now, you might go, well, that definition for mutually exclusive sounds pretty familiar, and it should, because it's the same thing as disjoint. Okay, mutually exclusive and disjoint are really the same things here. Now, if A and B are mutually exclusive, then they cannot be independent. And if A and B are independent, they cannot be disjoint or mutually exclusive. When do you use the rule for disjoint events? Is when we're adding probabilities, which means we need to see an or. And when do we use the rule for independent events? Is when we want to multiply. And our key word here is and. So applying our probability rules here. First example, a transatlantic telephone cable contains repeaters at regular intervals to amplify the signal. If a repeater fails, it must be replaced by fishing the cable to the surface at great expense. Each repeater has probability of 0.999 of functioning without failure for 10 years. Repeaters fail independently of each other, which means that if one fails, that doesn't mean that the next one down the cable from it has a greater or lesser chance of failing. This assumption means that there are no common causes such as earthquakes that would affect several repeaters at once. So part A says, find the probability that 2 repeaters function properly for 10 years. So really we're finding the probability that we get 1 repeater that works and a second works. Well, can we just do the first repeater times the second repeater? Can I just multiply the individual probabilities? And I can only do that if the events are independent, which they told me in the problem above that they are. So what's the probability that the first one works? Well, 0.999. What's the probability that the second one works? The same thing, 0.999. So all I have to do is multiply those two probabilities, and there's my final answer. Let's do this instead. There we go. So really I'm taking 0.999 squared, which still puts me at a very high probability of 99.8% essentially. Find the probability that 10 repeaters function properly for 10 years. So we have the probability that the first works and a second repeater works and yada 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 and the 10th works. So there's really 10 things going on in here. And we can just set that equal to, again, that the first works times the second works times ... all the way up to the 10th works. So if you think about it, we're really taking 0.999 and we're multiplying it by itself 10 times. So we could just say that that's 0.999 to the 10th power. And that is equal to somewhere 0.99004. So we're still at 99% chance here that 10 repeaters will still work after 10 years. So part C, the last one here. The transatlantic cable has 300 repeaters. Find a probability that they all work properly for 10 years. Well, we can multiply the probability that the first one works times the probability that the second works all the way up to the 300th. So we're really taking 0.999 to the 300th power. And man, when you start getting many 0.999s and start multiplying them, they really start to work their way towards 0. Okay, so we're looking at a little over 74% chance that all 300 repeaters will be fine in a 10-year period. So we're looking at there's about a 26% chance that we're going to have to replace at least one at some point down the road. And one more example here. It says the letters of the word statistics are placed on index cards and thrown in a bag. List the sample space. Okay, so what letters could you pull out of this bag? Well, we don't want to include repeats. Okay, so we could pull out an S, we could pull out a T, an A, an I, and a C. Those are the only 5 unique letters that make up the word statistics. So our probability distribution, or our probability model that we talked about in the second video, here's all my 5 outcomes. And now what are the probabilities? Well, the probability of getting an S, well, there were how many S's in the word statistics? 1, 2, 3. Out of how many letters altogether? 4, 5, 6, 7, 8, 9, 10. So I have a 3 out of 10 chance, which is 0.3, 30%. Now what's the probability that I get a T? Well, there's 1, 2, 3 T's as well out of 10 letters, so 30% as well. A's, there's only one A out of 10, so 10%, 0.1. I's, there are 2, so 20%, 0.2. And C, there's only that one, so 0.1. And again, if I were to add all of my individual probabilities up to make my sample space, that should give me my 100% or 1. So last but not least here, let the event V that we have a vowel, and I would hope to goodness you guys know your vowels, right? A, E, I, O, U. We're not going to include Y here. And the event M is that the letter falls in the first half of the alphabet between A and M. So list a sample space for each and find the following probabilities. So for V, vowel, well, what letters up in our probability distribution or our probability model are vowels? Well, those would be A and I. What's the probability that we get a vowel in statistics? Well, we can just take our two separate events here and add them together. So 0.2 and 0.1 makes 0.3. M. What's the event M that we get a letter that falls in the first half of the alphabet between A and M? Well, S is not between A and M, and certainly T is not. A is, and I is, and C is. So A, I, and C represent our sample space for this event, and the probability would just be those three things all added together, because A, I, and C are all disjoint events. You know, there is no overlap between A and I. There is no overlap between I and C. They're individual unique letters. So 0.1, 0.2, and 0.1 makes our 0.4. V or M, that we have a vowel or it falls in the first half of the alphabet. Well, we can just really look at our two events here and see, well, what do they have in common? Well, not what they have in common. What do they have all together? Well, they have A's, they have I's, and there's a C. So A, I, and C would be vowel or in the first half of the alphabet. And that probability is, well, it's the same as what it was for just M, right? So it's still 0.4. This sample space is the same as this sample space, so the probabilities would be the same exact thing. And the last one here, M complement, that it doesn't fall in the first half of the alphabet. Well, those were our S and T's. So that is our sample space. And now what's the probability of that happening? We can add together the 0.3s, or we could come down here and take 1 minus the probability of that event. So 1 minus 0.4 gives us our 0.6 that we also get from 0.3 and 0.3. And that is all for the fourth video, and we will see you in the fifth video.
All right, and the last example. The daily number big 3 has been rigged. The even-numbered balls have been made lighter so that they occur 3 times as often as the odd-numbered balls, which are equally likely to occur. So first we're going to construct the probability distribution. Okay. Now, the daily number here, they just use the numbers 0 through 9. Okay. So we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our sample space. Now the probability. If things were truly equal, well, then every number would have a probability of 10% of occurring. But they're saying the even-numbered balls aren't going to be the same as the odd-numbered balls. So how are we going to figure out what that probability is? Now occasionally you're going to have to do a little bit of algebra to figure out problems like this. So let's run through this together here. Now the even ones are 3 times as likely to occur as the odd ones. But what's the probability of an odd one occurring so that I can multiply it by 3 to get the even? We don't know. So let's call the probability of an odd-numbered ball x. And it says that each are equally likely to occur. So each odd will assign a probability of x. Well, then an even number is 3 times that much. So that means the even numbers must be 3 x's. Okay. Now, we go back to probability rule number 2, that the probability of your sample space, of all your sample spaces occurring, needs to be 100%. So what is 3x plus x plus 3x plus x plus 3x plus x plus 3x plus x plus 3x plus x? Well, let's see. Here I've got 4x, and I've got 4x 5 times, which makes 20x. So I have 20 x's that need to equal 1, or 100%. Divide by 20, and each x has a 1 in 20 chance, which is the same thing as 5%. So now let's go back up here. So all my x's, all my odd numbers, have a 5% chance occurring. And all my even numbers are 3 times that much, which is 15%. And if you added up all those 15s and all those 5s, all the 15s are going to add up to be 75, and all the 5s are going to add up to be 25, and 75 and 25 makes 100%. Now, it says A is the event that an odd number is drawn. Find the sample space of A and the probability of A. Well, an odd number is drawn. Those are our odd numbers, 1, 3, 5, 7, 9. And the probability that we get an odd number is the sum of their individual probabilities. Because we're not saying that we want a 1 and a 3 and a 5 and a 7 and a 9. We're saying a 1 or a 3 or a 5 or a 7 or a 9. So we're going to add and not multiply. So 5, 5, 5, 5, and 5 gives us our 25%. For part C, it says let B represent a prime number is drawn. And again, this is where I always assume that everybody knows the definition of a prime number. That it's a number that goes into itself or the only numbers that can go into it are 1 and itself. But those two things, 1 and itself, cannot be the same. So 1 is not prime, nor is it composite. It doesn't fit either. So your prime numbers up here are 2, 3, 5, and 7. Okay? 0, 1 can go into 0, but 0 can't go into itself. That's undefined. So the probability of a 2, 3, 5, or 7. Well, 2 is 15%, plus 5, plus 5, plus 5 is going to give me 30%. And are events A and B disjoint? Okay, disjoint means that they had nothing in common. Well, do these two events have nothing in common? No, they've got outcomes in common. They've got 3, 5, and 7 in common. So they are not disjoint. And that is the conclusion of the notes finding. Thank you, and good night.